Good evening, good morning, good day, good afternoon, good night, whenever you're listening to this. This lecture is about comparing means. So we will be covering chapters 11 and 12, which deal with two different types of t-tests, which is a very popular, widely used type of statistical test when dealing with normal distributions. So this is a parametric test in which we want to just compare the mean of two different groups. Those groups can be very different, as in like totally different individuals or uh, data points, or they can be two different groups, but the same individuals that you measured at time one and time two. So the language that we use can be a little tricky, but basically what we're doing is what we're doing is coming up to the end of this semester in this Introduction to Behavioral Statistics course. So all semester long, I've been talking about how descriptive statistics lead to inferential statistics, and that you have to have certain levels or scales of measurement in order to do certain types of inferential statistics. So here you can see that if you're not able to calculate a mean, you wouldn't be able to do a t-test that compares the means of two different groups. And you need the interval ratio level of data in order to add up all of the naturally existing numbers in a data set in order to produce the mean and also to produce the standard deviation. So the standard deviation is used when we are dealing with the normal distribution, so we can kind of tell in a relative sense how far apart different data points are. And this is a test that directly uses these ideas. So that's why I've been saying in all of my lectures that you really do need to master the material at the beginning of the semester to thoroughly understand what it is that we're doing here at the end of the semester. We are starting out in our textbook, which I have abridged or edited down for your convenience. It's located, I believe, in the week 14 module on our Moodle course. So the test three notes, the course textbook, the abridged version are located there, as well as you will find quiz 3 and test 3. So test 3 will be the final exam for the spring 2024 semester. We will take it on Moodle. You will not be taking it wherever the official schedule says. So we will be taking it, though, during the allotted time. So it will be from 2 p.m. to 4 p.m. It is cumulative. That means it's going to cover all of the material that we have covered this semester. This is important, especially for a course like this, because as I've said several times, this information is naturally cumulative. As in, you wouldn't be able to understand why we're using table B2, which we'll be using today, t-values needed for rejection of the null hypothesis, unless you understood what a null hypothesis is and what it means to reject a null hypothesis. Furthermore, would you really understand what this signifies right here, df, if we hadn't gone through that material in chapters 5 and 15, and we'll return to it again in chapter 11 today. So these are the degrees of freedom that you need to locate the critical value in order to tell whether your obtained value has surpassed the threshold for rejecting the null hypothesis, retaining your research hypothesis, and therefore providing evidence that the data that you're looking at are not due to chance alone, or at least not likely due to chance alone. So we will be moving throughout the textbook. As you can see, I've condensed it. It's much shorter than the other version of the book, which is the full book. I just went in and deleted all the pages that we're not using this semester. So this is a smaller file. It should be, I think, easier to manage for you in some regards. So we will be starting out in chapter 11 today, moving through all of this material that we've covered this semester. Take note as well that I've given you my copy that has the highlighted material in it. So along with what I think the textbook author does really, really well, which is provide you these very convenient tables such as this, like explaining what the null hypothesis is, how that relates to directional and non-directional hypotheses, what the science and terminology are, these tables do a really just fantastic job at summarizing and condensing a lot of complex information. So I've tried to highlight for you the information that I also think is worthwhile paying specific attention to, but don't rely upon that solely. You really do need to take the time to move throughout the book to really try to truly understand the material. For example, like the final exam will be cumulative, and I will expect that you already know what a test statistic value or obtained value is, what the critical value is. So when I use that language, you should be familiar with that to the point where I can ask you a complex question such as, how would you find the critical value for a t-test? And I could have a series of possible answers. But the correct answer is in a table that tells you, based upon the degrees of freedom and the significance level that you have, 0.1, 0.05, or 0.01, that's where you would locate it. So I want you to know stuff like that. So as I've said several times, like I think the textbook is laid out really well. This I would have put probably a little earlier in the book because it's really a fundamental concept that's really difficult for a lot of people to understand. So the bell curve or the normal distribution has certain features to it. It just exists in a certain way. So it's symmetrical. It has asymptotic tails, which means they stretch out forever. And it has 3 standard deviations away from the mean, because if you go much more beyond that, you can go off into infinity. But if you go much more beyond that, it doesn't make a lot of sense substantively, because eventually you'll have 99.999% of all data that you could ever collect, and you're very much not likely to go farther beyond that. But what we're doing is we are trying to obtain a value that is larger than the critical value. So when we go to this table and we identify the degrees of freedom, which are directly related to the sample size or the number of data points that we use in the calculation, we find that let's say that we have 100 data points, okay? We have a two-tailed test. That means that we are using a non-directional research hypothesis. It could go this way, it could go that way. We don't know yet. We're just kind of wink, wink, nod, nod, pretending sometimes, but sometimes we just don't have enough literature or substantive arguments to convince an audience that we are justified in using a one-tailed test, which makes things easier on us. Compare, for example, 63.657 over here on the two-tailed test to 31.821 over here on the one-tailed test. It's easier to reach statistical significance on the one-tailed test than it is on the two-tailed test. So let's go down to 100 degrees of freedom at the 0.05 level. So this is the standard significance level. It's the 95% confidence level, where we say we're 95% confident that our results are not a type 1 error. So if you had 100 respondents, you have to reach 1.984. So 1.984 would be that score that you're looking for, that you want to get past. So again, imagine that 1.984 was here, which actually it's about right here. We need to have a larger obtained or statistical value than that. So that's what this table is useful for. Now this number right here, see how different this is? Like, we're counting up to 100, and then we have the word infinity. So as you go further and further and further away from 0 and closer towards infinity, you'll basically approach a number 1.96. This is kind of the magic number that a lot of people use and a lot of people memorize. This is probably right here is what they're talking about, with the assumption that the sample size is sufficiently large to approximate a bell curve. So as I've said before in this class, your data will not always reflect a perfect bell curve. And a lot of that, though, has to do with the sample size that you have. Like, the larger the sample, the closer the shape of the data will be to a normal distribution. And if that's the case, then we can make certain assumptions, such as that 1.96 is our critical value, unless you have smaller sample sizes. But look at this. So 1.96 to 1.84, 1.86, 1.87, 1.89. Okay, I mean, these are like really close here between 85 and 100. And that's like 15 people. So let's say that you had to have a sample of 100 people. And it just takes a lot of money and a lot of time to get each individual person. You get up to about 85 people. And what's the real difference between 85 and 100? So it's literally 0.005. That's 5/1000ths of a difference. It's a very, very small difference. Now, as you go farther and farther away from infinity and get closer and closer to 1 degree of freedom, you can see that the critical values jump drastically. So if you have 1 degree of freedom, which means like you have a very small sample, the obtained value that you have to achieve is very high. Like this is a very large obtained value. And especially if you want to have 99% confidence that your data are not just due to random chance, this is just nearly impossible. But who knows? It might have been achieved sometime. But look at this leap between 1 and 2. This is a drastic leap. But as we go closer and closer to infinity, the leap or the distance or the difference between these critical values shrinks. So the gap is shrinking between these numbers. You can look for yourself and think through this. So we get to about, let's say, 60. 60 is kind of the cutoff point for sociologists. That's a pretty good sample size for a lot of psychology studies. I've seen a lot of psychology studies have a benchmark of about 30. And you know that you have to use an unbiased estimate because when you have a smaller sample, your standard deviation depends upon the sample size, and you want to be more conservative. So essentially, you're kind of increasing the difficulty on yourself. And that's the benchmark of science, is we want to kind of at least pretend like we don't want to be right. It's like when a small child really wants a gift and they're just, well, I don't really know if I want the gift or not. They want it. So we want to support our research hypothesis. We want to reject the null hypothesis, but we also keep in mind that our audience could be highly skilled, highly trained, well-informed, very smart other scientists and readers who know a lot of the little tricks about how to fudge the numbers. So, we can use like 60 as a benchmark, and we're pretty close to like the whole number 2. So I imagine the whole number 2 looks like it'd be about 61 or 62 here before it leaps over to 1.997 or 1.999. Here you can see like the difference is so small. This is in the thousandths, like very, very, very tiny differences. So as you get closer to infinity, we have this number 1.96. So typically 1.96 is the widely accepted critical value of studies that have sufficiently large sample sizes. So 100 and beyond, you're getting pretty close to 1.96. So 1.96, get it? Okay, so returning to the book. When we're doing statistical tests, we want to have we are typically looking to support our research hypothesis. So we want to produce an obtained value, the result of our statistical test, that surpasses the critical value. But if you recall from chapter 10, that's not all we're doing. So chapter 10, we did a z-test where we compared the mean of the sample to the population mean and divided by the standard error of the mean, which itself is composed of the population standard deviation divided by the square root of the sample size. Now, I've said this before. I'm not the type of person who would have ever come up with this on my own. I get the formula and I can be told what to do like a recipe book. But for me, I would not be able to answer the question, well, why, Dr. Ellifritz, is it the square root of the sample size? I would say, I don't know, because it makes the sample size smaller, by half or something. I'm like, I don't know. 2 things. One, you would not be able to do a z-test, compare a mean of a sample to the mean of a population unless you had that data about the population. Oftentimes in inferential statistics, what we're doing is we're trying to infer from a sample to a population because we don't have the data about the population itself. So, secondly, I want you to recall this, that a lot of the lower level statistics, like the descriptive statistics, the mean, and the standard deviation, are necessary to calculate in order to do higher level statistics. And it's those higher level statistics that are going to allow us to make judgments. So if you have to make an important decision, you probably want to be fairly confident in your decision. Well, the mathematics of statistics can help you make decisions, can help you differentiate between whether or not you should have seen something or shouldn't have seen something. And that depends upon the study, the data that you're looking at, etc. But remember this, that not only are we comparing, or are we inferring from samples to populations most of the time and running our null hypothesis and doing our procedures to produce an obtained value and ascertain whether or not that is statistically significant, but we are also trying to understand whether or not the differences are real, whether or not there's a measurable effect size. So statistical significance simply means that we have a certain confidence level, typically 95%, of whether or not we've made a type 1 error, a false positive. But that tells us nothing about the magnitude of difference. It doesn't tell us whether or not it's a meaningful difference. So the effect size tells us whether or not it's meaningful, and that's something that we'll return to again and again. So here we calculated Cohen's d. It was very simple. The sample mean compared to the population mean divided by the population standard deviation. And then it gives us a coefficient that we have to kind of compare to other results. And there's kind of a general rule about the size of the effects. And then you'll use language to communicate this to other people. There are very smart mathematicians and statisticians and quantitatively literate people out there who can look through all of this kind of stuff and kind of immediately know just from the numbers and the calculations. Here, Jacob Cohen's book, Statistical Power Analysis for Behavioral Sciences, believe it or not, there are people who write and read these things like for a living and for fun. I've heard them talk. These people are super smart and super nerdy. So hats off to them. They are helping all of us achieve a better world. So I say that in jest. So we are returning to chapter 11. This is one of the two different types of t-tests that we'll look at in this lecture. The t-test for independent samples is about two completely different groups. So think about boys and girls, or think about men and women, or think about married versus unmarried, or people with college degrees, without college degrees, part-time versus full-time, or employed versus unemployed. So completely different people, like people who cannot occupy the same category at the same time. So you might be interested, for example, like psychology majors compared to nursing majors. And maybe there's a double major in there, and you kind of, need to be careful for that and take account of that in your survey. Are you a double major? No, yes or no? So what we're doing at the end of the day, though, is we are using a mathematical formula to produce a statistical result that we will compare to a known critical value that will help us establish whether or not we have statistical significance. If we do have statistical significance, then we go on to establish the meaningfulness, or what's called the effect size. So don't let anybody fool you by saying that something is statistically significant. You should go, and? Like, don't say so what, say and. And if they say and what, you say what's the effect size? What's the magnitude of the difference? That's part of being quantitatively literate. Okay, so for the exam, I would expect you to know something like this, that there was a t-test conducted. At this point, you don't know whether it's an independent sample or a dependent sample. You'd have to read that from the context of the situation. There are 544 degrees of freedom. See my previous lecture on degrees of freedom. The obtained value is negative 4.19. So the absolute value is 4.19. So here, remember what I said about how numbers larger than 100 kind of are approaching infinity? So what do you think the critical value would be that we would need to surpass with this? Like, Can you tell just from this information right here, like you might need to do on the exam, know what I'm saying? Can you tell just from this whether or not it's significant? Well, yeah, because the p-value is less than 0.05. In fact, it's less than 0.0001, which is really significant. Does that really matter if it's, I mean, yeah, I mean, you're very much not likely to have made a type 1 error, but it doesn't tell you anything about effect size. So we have 544 degrees of freedom. Let's go to our table. We don't have 544 degrees of freedom. It just goes from 100 to infinity. Well, okay, so that's where the magic number 1.96 comes in. So if on the exam, if I left this out, or even if I left that in there, would you be able to tell that this is significant? I would. Now, if this were 54, I would say, yeah, this is most likely significant because I think 54 is somewhere around like the 1.9 mark. I don't have all these memorized, but yeah, or it's at 2.004. Okay. So, I don't have all these memorized, but I have a general sense about where the critical values are at. So this is the kind of stuff that you need to know. So you need to start becoming, kind of nerdy like these people, Jacob Cohen, who writes Statistical Power of Analysis for Behavioral Sciences, and start developing your knowledge and understanding of this type of material. So again, we are looking at two different groups with an independent samples t-test. With a dependent samples t-test, the math changes, the research question and a hypothesis change, because we are now looking at kind of the same group in two different instances, or group 1 and group 2 are just time 1 and time 2 of the same people. The language really depends upon the audience and the research report. I don't want to teach just that there's one specific way that we always do things, because it really depends upon the field of study, the discipline, the journal, particular scientists. Okay, so the path to wisdom and knowledge. Almost every statistical test has certain assumptions that underlie the use of the test. This is something that I went over in the previous lecture, that the assumption here is that since you're dealing with two different groups, and we want to compare the means of the two different groups, okay? And if you just look at a normal distribution, you should know the mean is directly in the center. Like here, we can look at these two different groups, and the curves look the same. Like if I were convinced that these curves are actually visually representing the descriptive statistics, I would say, okay, yeah, this has met the homogeneity of variance assumption, that the two groups are not different because of their standard deviations or because one has more kurtosis or is skewed. If one of these curves were skewed and the other one had really thin kurtosis or something like that, I would say, well, we can't compare these groups because they're so different anyway that the difference in the means could just be internal fluctuations due to some other thing that we're not really looking for. So you want to make sure that your groups are comparable. You want to compare apples to apples, not apples to oranges. And if you are comparing apples to oranges, your variable should be fruit. Okay, so as we mentioned earlier, there are 100 statistical tests. The only inferential one that's used, one sample that we cover in this book is the one sample z-test. I just want to mention this because there are many, many different types of tests that we're not talking about in this course. My job in this course is simply to introduce you to the fundamental or foundational concepts in statistical research or statistical analysis. So do keep that in mind. Another thing that I want to do in this course is introduce you to the symbols and the notation that would be used in statistical and scientific analysis for the quantitative side of inquiry. So this is the t-test. T equals the comparison of group 1's mean with group 2's mean, or the mean of group 1 with the mean of group 2. That's what the subscript refers to as 1 and 2. And you should know at this point, if you don't know at this point that X bar means the mean of a sample, you need to go way back to the beginning of the semester and really work hard to catch up, because you're pretty far behind if you don't know what these symbols mean. Like if you don't know what this lowercase n means at this point, I've already mentioned it today once, you're pretty far behind. And I'm just being honest with you. You need to go back and you need to refresh yourself. So this is the comparison of two different means. So what I want you to do now is develop the confidence that you can look at something like this And even though it might seem like very complex and like full of stuff that you just don't understand because math is hard and complicated, you can get it. This is a comparison of two different means. That's the numerator. That's the thing that we're interested in. And the denominator of the equation is first and foremost the square root of. So one of the reasons why we're taking the square root is because we're squaring the variance. We are the standard deviation. So because we're using the variance instead of the standard deviation, we're going to take the square root of this. So the variance is helping us to measure the internal variation of these two different groups, whether or not they're different or the same. So we're accounting for that. Now we have to make sure that in the first place they're comparable, but then the mathematics also take care of that for us. And then look, we're basically just looking at the sample size minus 1, so that's degrees of freedom. Here's the degrees of freedom. Sample size plus sample size divided by sample size times sample size times. So it gets very complex. And believe me, you can do this all by hand. If you had a sample size of 100, you kind of don't want to do that because you have to calculate all of this kind of stuff. It becomes very complex. But this is a bigger formula than we've seen before, but there's really nothing new here at Values. Okay? So if you had a large sample size, or if you had a large sample size, but a large data set, then this can be very tedious to do by hand. So thank goodness our computers do this for us. But the procedures are the same that we've done all semester long. So we have a null hypothesis that uses the population level notation. Remember that. So this is the population mean of group 1 versus the population mean of group 2. Now, this is kind of an assumption. We don't, like I said with the z-test, we don't oftentimes have the data about the population. In fact, that's the whole point of taking a sample, is so that we can infer from the sample to the populations. If we had data about the populations, we could run z-tests, or maybe we don't even need to do this statistical analysis. We could just get straight to the effect size. So one of the reasons that we do inferential statistics is because we don't have all the time and money in the world to spend on gathering all the data, and sometimes it's not available. So we make certain assumptions, and the assumption is that without further evidence, the null hypothesis is true. So we are trying to provide evidence that our research hypothesis is supported from our sample. We can never say prove in that case because we don't have all the data. We're simply making an inference based upon the recognition that 5% of the time we could be making a type 1 error. So that's how this works. And if what I just said makes sense, congratulations. You've been following along. You're probably doing great work. If what I said doesn't make sense, you need to go back and you need to review the material and really kind of catch up. Okay, so we are typically setting a 0.05 or 95% confidence level. We are looking for an obtained value that surpasses a critical value that we find in a table like this, typically with sufficiently large sample sizes. We already know it off the top of our heads. It's 1.96. And we plug in our numbers. So here I've highlighted in green the variance. Okay. So this is about the only thing that I didn't cover in depth. At the beginning of the semester, I did say that we would use this toward the end of the semester. It's basically just the standard deviation already squared. So I'm not quite sure in the book why it is that they still have the square above it, whether or not they meant to do this. There are some errors throughout the book. So if you do catch some of that stuff, you can always send me an email and I'll try to help explain and I'll dig down into it. But basically the point is that these are just the numbers from the tables up here. They plugged them in, and they're going to produce a t-value. Okay, so the t-value here is negative 0. Can you tell whether or not this is significant? Have we surpassed the 1.96 level? If you don't understand yet, the negative can be treated like an absolute value. You just say the absolute value because typically we're dealing with a two-tailed test. So either side of the test, the positive side or the negative side. So this has clearly not surpassed that goalpost of the 1.96 critical value that we set as our confidence level for the 0.05 level that we traditionally work with. So what the rest of this is telling you is, okay, in order to find that, you have to use table B2 and appendix B in the back of the book. When I switch over to this tab, I've already just set it up to be in the back of the book. So that's what it's jumping to, table B2. So you use the degrees of freedom, which again is a concept that says that the degrees of freedom are how many options you have before you absolutely know what the last option is. So how many aces can you fold over before you know what the last ace is? So you have 3. So you have 3 degrees of freedom because you flip 3 over. You automatically know what the last suit of that, or the suit of the last ace is. So there's a pretty good explanation here. For this one, it's just n-1 plus n-2. So you're just taking the sample size -1 of group 1 plus the sample size -1 of group 2 and then adding them together. So that's how you know. So typically, since you're dealing with a t-test, it's 2 different groups. You just, whatever the degrees of freedom are, add 2 to that, and that's the sample size. Okay, so do read through this material. I'm not going to read and go over every single word. What I want you to know is that this was a t-test. There were 58 degrees of freedom, so the sample size was 60. As in, I know that the sample size was 60 because put into parentheses here next to the symbol for the test that was done, I just add 2 to it because I know what the test is and I know how to calculate the degrees of freedom. That's the kind of stuff that I want to see you be able to do on the exam. The obtained value is 0.14, and this is not significant. We know that because P is greater than 0.05. We should know that by now that 1.96, especially for kind of larger numbers, but really 58, you're around 2. You gotta get to 2. So this is pretty far off, not significant. You're likely to have made a type 1 error. Don't worry about this data. But now we want to worry about the effect size. So here, let's pretend that the example does have statistical significance, okay? So we're returning to effect size. Here, we have the mean of group 1, no community service, compared to the mean of group 2, with some community service. So here, notice that the standard deviation is kind of different, right? 1.03 versus 1.53. That's kind of a pretty big difference. That's, that's a judgment call whether or not you want to say that the assumption of the homogeneity of variance has been met or not. If we go back up here to what I highlighted, 3.42 compared to 2.06. Again, it's a judgment call. Like whether or not you as a scientist would want to accept that, or if you want to overlook it. Again, I'm not sure why they left the exponent of the 2 here. Maybe it was to indicate that it's the variance. I'm not sure why they did that, or if they're just plugging in the values themselves. But the point is that, those are the things that you want to look at and look out for. And at this level, I just want to make you aware of it. But at the, at the technical level, at the expert level, those are definitely things that people pay attention to. And sometimes it slips past the editors of articles and the reviewers of articles, and it gets published. And then later on, somebody well, hey, you violated a pretty basic assumption here. We got to go back and test this again. Oh, look, we can't find support for your study. Okay, so the effect size. Well, once again, we are just using a kind of a simple formula, okay? So the mean of one group compared to the mean of the other group divided by a standard deviation. Now here they've used the mean of group 1, no community service, I believe that is community service, compared to the group with no community service, okay? So it gives us a nice whole number. That kind of makes sense. But then they use the standard deviation of the group with community service. Like, why not use the standard deviation of the other group? How do they come to that conclusion? Like, why is it that we're using one versus the other? If we were going to end up with a negative number, should we use the standard deviation from that group? I don't really know. Like, it's a judgment call. So they don't tell you in the book why they do this. It's just you saw from the guidelines, that the result 3.66 is kind of a medium size. That there's a fairly large difference between these means. So imagine that you are working for the government, or that you're working for the university administration or some employer, and they want to know, okay, should we hire, or are there effective programs, or does having community service versus no community service affect a neighborhood, or affect employment, or affect aptitudes, or something like that? Go. And by the way, your job depends upon this. Like, if you give us bad results and we misinvest or misallocate our resources, you're not going to get that promotion. In fact, we might have to fire you because we've just lost a bunch of money. So we need to know. Now, let's say that you did a t-test of independent samples and you found that there's a statistically significant difference. Since you've taken this course, you know that that's not enough. You know that there is a difference, but now you need to know whether or not the difference is sizable, whether the magnitude is of such difference that there's not just something statistically significant, but there's something remarkably different about these two groups. Now, this is saying, yeah, kind of, that, like, whatever the measurement was here, the mean of, I don't know how these means are exactly being calculated, but yeah, this is a meaningful effect size. Sure, that's nothing to shy away from. You might get that past some people who don't know what they're talking about, but if you got me on your committee, I'm going to look at this and I'm going to say, why'd you calculate it like that? And if you can't answer my question, I'm going to look to my right, or I'm going to look to my left, and I'm going to say, like, I don't know if they know what they're talking about. I think maybe they just use some AI program in their Excel spreadsheet, and they're just, maybe blowing smoke. Because here's another way to calculate the effect size: is you compare group 1 with group 2, and then you divide by the population variance, or so you compare group 1 to group 2, and then you divide by the variance of the two different groups. So now we're doing something a little bit different. This gives you a little bit more precise results. So here you'd get a whopping difference of 0.4, and that's bigger than 0.37. But if I challenged you and I said, I'm like, why'd you pick this number versus that number, and like why the standard deviation of one versus the other? If you stood there and you said, I don't know, I've seen this happen to people in committees and presentations. Is somebody in the audience knows what they're talking about, and the person presenting it, they're just presenting on a report that they took part in, but somebody else did the statistics. So you want to be able to answer this kind of stuff because some people know what they're talking about. But if you then said, oh, well, okay, yeah, I did use a more precise formula, and the effect size was not very different. Okay, I'd be like, all right, fair enough. Or you can try to make the case that 0.43 is drastically different than 0.37. It's up to you. But just know that there are different ways to calculate different components of statistical analysis. One thing that we're not even going to get to in this course are post hoc tests. So post hoc tests are done once you have your analysis and your statistical analysis, your effect size and everything. Then maybe we'll want to know something a little bit more in detail or in depth about the study. So lots of stuff that we're not going to get to this semester, but I'm trying to introduce you to some of the basics and some of the more widely used tests. This particular test is really good if you are looking at a time 1 and time 2 occurrence. So let's say that you want to know the effect of implementing community service in a place where there was no community service, and you're thinking ahead. You go out before it's been implemented, and you do a survey of whatever it is: attitudes, knowledge, behaviors, feelings, stuff like that. Then you implement the community service, and then you go out to the same exact people at time 2 and gather the same data. And you want to see if there's been a measurable difference between time 1 and time 2. Now the groups are essentially the same exact people, But the difference is the intervention. So this is actually a little bit more experimental. The previous one is experimental if you have a control group versus the treatment group. So if one group has been left alone and the other one has some type of intervention and you've controlled for other factors, then you can do that t-test. This t-test is really good for the same group before an intervention and after the intervention. So that's when you want to use these types of analyses. Okay, so this is a fairly short chapter because we already have a lot of stuff under our belt. We already know that we have to produce an obtained value with a particular type of test, that we have to use the degrees of freedom to locate the critical value. Typically with sufficiently large sample sizes, it's going to be 1.96. But, still you do want to be a little bit more precise. If you have like 55 in your sample, then it's, going to be a little bit more difficult to reach that critical value. But, it's essentially the same type of stuff. Okay, so these flowcharts are very, very handy. Are you examining the difference between variables or groups? Okay, I'm examining the difference between groups of one or more variables. Are the same participants being tested more than once? Yes. How many groups are you dealing with? 2. So t-test for dependent samples. In the future, when you're doing studies or you're doing research, this table can help you immensely because you're going to think like, okay, now I've collected my data, what do I do now? And this flowchart will guide you through what it is that you're supposed to do. Okay, so here is the formula. Now, remember that this sigma means add together. So D is the difference between each individual score from point 1 to point 2. So let's say that you have a group of 5th graders, like a single group of 5th graders. And at the beginning of the year, you want to measure something like emotional maturity, right? You're just interested, like what does Mrs. Adderley's class do to the emotional maturity of this group of 5th graders? So you measure emotional maturity however it is at the beginning of the year. Then at the end of the year, you take that same group of kids and do the same study. Now, as you recall from the chapter on validity and reliability, there are some issues that you can run into because you're measuring the same people at 2 different times. So there's issues of autocorrelation and other factors, because shouldn't you expect to see the same people to have kind of similar scores? So in some situations, the scores can be very subtly different, which means that the effect size might be altered, but those are all kind of deeper statistical issues. At this point in time, we're just adding together the difference of the same people at 2 different times. So, you would code the students to anonymize them, and you just find that same coded number with the kid, maybe their student ID, and compare that particular individual. Then you divide it by the sample size, so the number of paired observations. So we call this like paired observations. So just think about this as in like you have one person at time 1, time 2, another person at time 1, time 2, another person at time 1, time 2. How many of those people do you have? It should just be the sample size. You should have everybody at time 1, time 2. But maybe you have attrition. So somebody moves and goes away to a different school. Or maybe you have the addition of another student. So now you have somebody present at time 2 that wasn't there at time 1. Well, they have to be left out of the study because you can't measure them twice. So the sample size times the addition of all of the differences squared minus the addition of all the differences squared divided by n minus 1. So essentially the degrees of freedom. Again, I don't need you to know the math. What I want and I hope at this point is that you can look at something like this and feel confident enough that if you stare at it long enough, you can tell what's going on. Like what are they doing here? And a lot of the mathematical formulas just they have to do with what it is that we're interested in. So you have the same group at 2 different times. Okay, so you want to subtract time 1 from time 2. So you have the pre-test and post-test. So 3 minus 7 is 4. It's actually negative 4. But we're taking the absolute value here. 5 minus 8 is negative 3. So actually what they're doing here, I apologize, is they are subtracting the post-test from the pre-test. Because if we go down here, it's 7 minus 8 equals negative 1. I don't know why they set the example up this way. I would have done it the other way around. Anyway, The reason that we square it, again, we're returning to a concept that we talked about at the beginning of the course with standard deviations, because if you don't square it, we could end up with a negative number. And we don't really want to deal with negative numbers. They can be very problematic. So you square it, and you'll always end up with a positive number, because you cannot multiply two numbers together or two negative numbers together or two whole numbers together and get a negative number. You're always going to get a positive number. Okay, then you have down here at the bottom the sum. So you have, once we add up all these things together and we have all of the factors that are necessary for our formula, we just plug them into the formula. So then that's what they did here. You can run it yourself. What we have here is our obtained value. Now, is this significant or not? Can you tell just by looking at it? That's what I want to know. At this point, I want to know that. Yes, it is, because it is larger than 1.96. It's also it kind of behooves us to look at the actual degrees of freedom and the sample size. So here we have degrees of freedom being 24. Now remember, if you have a sufficiently large number, 1.96 is the value that you can work with. It's a rough estimator. Like if you're coming close to 1.96, most of the time you can be like, okay, but you wanna check and be sure. So let's check out where 24 is. So 24 is right here. This is 2.45. 2.45 is pretty far away from 2.064. And I know if you have dyscalculia, which is kind of like dyslexia for numbers, 2.05, that can kind of get jumbled around. But we have 24 degrees of freedom because there were 25 individuals in the group measured time 1 versus time 2. So subtract 1, you get 24 degrees of freedom. How far would we have to go up to come close to what we actually obtained? 2.45. 2.45. So it's the difference between 6 and 7. So 2.45, I would say 2.447, the 7 rounds, the 4 up to 05. That's like, quasi-significant. It's like right on the borderline. But I mean, you can have a fairly small sample size of 6 and still claim that this is a statistically significant number. So again, 1.96 can be your benchmark, but you need to go to the table, especially when you have smaller sample sizes. Okay, so then it would report the results. Again, if you saw something like this, you don't immediately know what type of t-test it is, but you do know that it's a t-test with 24 degrees of freedom. Once you know what type of t-test it is, then you can tell me what the sample size is. You have the obtained value of 2.45, and from this, you know that it's statistically significant at the 0.05 level because it's probability of less than 5% of making a type 1 error. Then you move on to do the effect size. Okay, so I want to leap over to the notes right now just to show you that in the notes, all of this information is condensed. You're not going to get as much detail from the notes that you are in the textbook. So you can start with the notes. If you've been doing that, carry on, but you do need to read into the textbook. So the interpretation of the t-test is fairly simple of these results. I just went over that. But the effect size is the same formula that you did for the test of independent means. You just take the measurement of the group at time 1 versus time 2, divided by the standard deviation, and that gives you the effect size. So again, we're not, a lot of this stuff, once you have it under your belt, is not that difficult. Okay, so that is the material for chapters 10 and 11. One thing that you want to keep in mind is the utility of these types of tables, because if in the future you are doing a study, you want to use the flowchart in the book, and these tables can be valuable to you. So this should be a file that you have somewhere, and I would suggest keeping it because Lord knows I got rid of my statistics books after the course was over, and I kind of wish I wouldn't have. But, that's a story for another day. Okay, until next time.